All right, today we are discussing lossy compression. So first off, can you guys tell a difference between these two pictures? Can anyone see a difference there?
Not much.
Not really. I know I can't see a difference, but actually, the one on the left is 300 kilobytes, 360 kilobytes. The one on the right is only 110 kilobytes. So somehow this file is about a third the size of this file. How can this be? The answer is lossy compression. So last class we talked about lossless compression, where the data can be restored to its original state perfectly when we decompress it. Lossy compression is what happens when we throw away data in the compression process in order to save some space. And in many forms of digital media, we can lose quite a lot of data without having the result be noticeably different from the original. So, some pros of lossy compression. The compressed version is significantly smaller than the original. And lossy compression is generally even better at creating smaller sizes than lossless compression, because if we can lose data, we don't have to compress it. It's just gone. So we can get even smaller than with lossless algorithms. And often the data that's lost isn't even noticeable by our human eyes and ears. We can't even tell that any information has been lost. So there's not really a detriment to it. A downside of lossy compression is when we decompress the data, it is no longer going to be identical to the original. It's still very close though, so it's not as much of a con as you might think. So algorithms that perform lossy compression are much more common than ones that perform lossless compression because of the size savings that lossy compression offers. There's so much more size savings offered when we get rid of data that being able to perfectly replicate our original isn't as worthwhile. Some common lossy compression algorithms. Images use JPEG very commonly. MP3 is used to compress music, and MPEG-4 is used to compress video in a lossy way. Just like we discussed last class, each of these has a separate file extension, which is going to indicate what kind of compression is being used. JPEGs use either .jpg or JPEG JPEGs. MP3s use a .mp3, and MPEG-4 uses .mp4 type files. So these files are generally going to be much smaller than the raw version of their original thing. So a JPEG is almost always going to be smaller than PNG is another type of image file, which is much less lossy in its compression. Now, lossy compression algorithms are most commonly used on images, audio, and video. And that's because there are elements within each of those things that our human senses won't notice when they go missing, whether it's a really high or low frequency, whether it's certain amounts of brightness, we won't really notice if they disappear. Lossy compression is much less common when working with text because it's way easier to tell when there's not information there when we're working with text. So one possible lossy compression algorithm for text is removing all of the vowels in a string. So can anyone tell me what this reads?
Can you read what this text is? I don't know what SYS is.
All right, but what does the rest say?
Without vowels.
Without vowels, all right. So can you read this text, what this text says without vowels? So we can interpret it pretty well, right? It's not impossible to read, but it is a little bit more difficult. So using an algorithm like this can sometimes be useful. Our human brains are pretty good at interpreting words even when they're missing their vowels. So if we really need to save some space, whether when we're storing or if we're just sending a message and we have a limited number of characters, removing vowels can sometimes be an effective solution. If you're sending a text message and you only have a certain number of characters, it's likely that the person receiving the text message will be able to understand what you mean even without vowels. Now, this isn't the optimal compression for every piece of text because, like, what if you're writing a paper for an English class? If you remove all the vowels from that, your teacher's going to be pretty unhappy with you because your text is a lot more difficult to read than it would be if it did have the vowels. So sometimes saving space is not as useful as having a replicable outcome, having it decompress into the exact same data. When we are doing lossy compression with images, one common way to do this is to decrease the resolution. When you decrease the resolution, you're lowering the number of pixels being used to represent the image, essentially. So in these two pictures, we're using less pixels in the one on the right than we are in the one on the left. So we are saving a whole bunch of space. With these two pictures of a dog, the one on the left is 630 by 630 pixels, which it's got all these nice smooth lines. And the one on the right is only 90 by 90 pixels. Now, this is considerably blockier, but we can still get gist of what's going on in this picture. It's not completely unreadable. So there are certain situations in which the one on the left might be useful and the one on the right might be useful. If I have a limited amount of space, let's say I'm making a website and I have a limited amount of storage space for my website, I might want to use the one on the right because it takes up less space in memory and it still looks all right. It's easy enough to tell what that picture is of. But if I don't care about how much space I'm taking up, I might want to use this dog picture that is less grainy. It's less pixelated. It's higher resolution. I can actually see what's going on way better. Now, something to keep in mind is that pretty much all digital data is compressed somewhat, because we live in an analog world. Analog meaning there's not really hard ones and zeros, unlike digital data, which consists of only ones and zeros, on and off. The real world can have all kinds of in between. There's an infinite number of numbers in between 1 and 0, and there's all kinds of different information that's not super easy to replicate using digital data. And space is the biggest limiting factor when we are trying to approximate analog data with digital data. And the closer you get to representing analog data, the more space you're going to consume. So as you get closer and closer to storing analog, you're taking up larger and larger and larger space with your digital data. So in order to save space, we are already going to lose some information. It's very similar to in math class, if you have learned about taking the area under a curve. One way that we can approximate this is we can put little rectangles underneath each area, etc., and then zoom in on that. We're going to lose a little bit of information in these areas that we're not covering with a rectangle, but it's close enough. And as we add more and more rectangles, we're going to get closer and closer to approximating what the curve looks like. So it's very similar to how we are representing analog data with digital data, because there's not a perfect way to represent all of the analog data that exists in, let's say, a sound bite or potentially a color. But as if we don't care about matching it exactly, we can use a compressed digital version of the information to store it in our computers. Does that all make sense?
Yep.
Cool. All right. Then I will